Hello, everyone, again, and welcome to the DMSI YouTube channel. And it's truly a pleasure to actually have you all in this particular space. And in here, we're going to be exploring some things quite interesting in the world of general chemistry. And this is really critical because you need to be able to manipulate numbers and use those numbers to determine or infer various situations involving population. In here, we're going to look at how to actually use percent or ratios to determine the atomic weight of elements. And specifically in this question, we're going to be determining the atomic weight of chlorine and using mass spectrometry, looking at this question to show that the ratio of the natural occurring chlorine 35 to its isotope chlorine 37 is ratio 3 to 1. Now, how would you be able to actually determine the atomic weight of chlorine? This is actually where you need to actually come up with a plan. Always you need a plan to actually create a particular outcome. First is, what is the question giving me? So creating a plan implies that first, let's look at some of the terms that are actually shown in the question. One is that you need to be able to know what the mass spectrometry actually implies. And this actually shows the relationship between the relative abundance and that of the specific mass ratio with the charge of that particular particle. And so where this actually y-axis gives us the relative abundance of various elements that is detected, this is actually performed using a particular machine called the mass spectrometer. And the mass spectrometer actually has three compartments. One is actually the first compartment, which actually has the ionization step, where in this case various gas related particles, in this case we are going to be passing chlorine gas, and chlorine gas, once it enters the chamber, a particular, I would say, photoionized charge actually comes in contact with this particular gas, and as a result this ionizes the gas to become chlorine ion. And as a result of this actual chlorine ion goes through a second chamber, which actually is important for the separation of various forms of chlorines that you might come in contact with in terms of the number of neutrons, because of course the number of protons remains the same, for chlorine to remain the same. However, when you split chlorines into various forms, these forms are called isotopes, and we're going to talk about that in this particular video as well. So this particular chamber, which is the separation chamber, is where we actually have a specific form of slit that actually separates chlorine here, gas, which is ionized now, into different forms of chlorine. In this case, we have one type of chlorine that is actually released, and the other chlorine is actually released as well. So, depending on the isotope, this actually is then goes into the specific chamber where we have a detector that actually detects various amounts of that specific type of chlorine that goes in here. So you could have a really high amount of the same isotope of chlorine for this particular one right here. In this case here, according to this question, is chlorine 35, and this could be actually noticed looking at this graph where you have the highest peak in there, and then you have another one here, which is, in this case, we'll say chlorine 37, where the chlorine 37, when you plot it on a graph, it actually has a little small peak right there. And why do I have differences in the peak? The peaks actually tells you the relative abundance of that particular isotope in here compared to the other one. So therefore, as a result, looking at this question, it tells us the ratio of the amount of chlorines isotope wise that are actually present in here. One is that the chlorine 35 is actually, in this case, we write chlorine 35, amount is 3 based on the first number before the little columns, and then the other one, which is chlorine 37, is actually 1. So the ratio here is 3 to 1. So looking at the plan in this particular video, our plan is to actually come up with the following. First, you need to actually go from these particular ratios here, isotopes, and from the individual isotopes, you actually, with the help of applying ratios mathematically or applying percent, will be able to actually determine the average, and from your average you're going to finally get to the specific atomic weight of chlorine. And what does atomic weight means? Atomic weight here means that you're measuring the amount of grams that chlorine has in 1 mole. And in here we need to know what the amount of grams is, and usually this actually grams per mole is actually represented as the number we don't know, but it's G over mole is actually measured as atomic mass or atomic weight units. In this case here, it's going to be represented as U. So let's look at this and how we're going to apply this to our question in here. So first off is, you need to actually develop your first step to get to our solution. So the first step, go back to the drawing board, looking at chlorine 35 versus that of chlorine 37. This actually shows us that, hey, this is an isotope of chlorine, which if you look at it in terms of the A to Z symbol, A is going to be represented as, in this case, 35, which is, in this case, is called the mass number, and 17 is actually the atomic number. And for 37, chlorine here actually has the A value to be 37 and the Z value to be 17. So what you notice is that chlorine actually has this specific chemical characteristic, which is due to the 17 number here, which is actually known to be called the atomic number, where the number of electrons is equal to the number of protons for chlorine's neutral form. However, for 37 here and 35 actually makes them actually different in terms of the mass number. So where this here, the mass numbers are actually different, this mass number differences with the same atomic number actually makes us to come to a conclusion that both of them are actually called isotopes. And so isotopes is when the atomic number or the number of protons are the same, however the mass number or the number of neutrons in this case are different. So in this one here for 37, the number of neutrons, which has a neutral charge, will be equal to, in this case, 20. And on this side here, the number of neutrons will be, in this case, equal to 18. So this is how isotopes actually comes into play, and various elements, they have relative abundance for specific isotopes. There are some that are way more abundant than the other, which shows that the most abundant one is more stable compared to the other one. And in this case here, looking at the ratio, which we know coming into play, we know that the ratio for the 35 here is 3 to 1. And this here, when we take into consideration that we assume that these are the only two isotopes out there, that means here that 3 to 1 tells us that 35 chlorine or chlorine 35 is way more abundant, which means it's considered to be more stable than that of chlorine 37. So therefore, in this case here, using ratio as one method to determine our answer compared to the other method, which involves using percent, I would recommend, trying both of them for any form of isotopes that you might be given, and we're going to actually go from there. First off, let's start with percent, because of course percent gives us a long way to actually get to our answer. And in here, when you look at the percent, in this case of 35 or chlorine 35, we just put Cl 35 versus that of the percent for chlorine 37, we know that first the ratio is 3 to 1. And once the ratio is 3 to 1, the total of the ratios is 3 plus 1, which is equal to 4. So for this particular case scenario, it means that out of 4 particles, which I'm going to show right here, if we have 4 particles here, 3 of them, in this case here, we're going to represent them as orange, is actually chlorine 35, while the 1 out of 4 is actually represented as chlorine 37. So therefore, in this case, to convert from this particular number here to percent, what you have to do is actually multiply the, in this case, chlorine 35 amount, which is the specific number 3 over the total number of particles 4 times, in this case, when you have this scenario actually placed in 100 samples, how many of chlorine 35 you're going to have in 100 sample. So in this case, you multiply by 100, and you're going to get, in this case here, 75% of your samples to actually have, in this case, 35. However, for the other case here, which involves chlorine 37, in here, out of 4 particles, we have 1, which means that 1, which is the specific number of chlorine 37, divided by the total number of particles, in this case 4, times, in this part here we have 100, and we're going to have 25 to be our number of particles that are chlorine 37 that will actually be present in 100 samples. So 25% will have chlorine 37 in this particular case right here. Once you have your percent, in this case, you are able to go from ratio to percent, and then to go from percent to the specific amount. What we have to do in this case is, since we know that in here, out of 100 samples, 75% are actually chlorine 35, and in here we have 25% to actually be chlorine 37. What we have to do is then get the average of these particular numbers here. And to get your average, all you have to do is, first, the total number of particles will be at the denominator, which is in this case 100, and it means that 75 of the particles are actually chlorine 35, which means that the average weight will be 75 times chlorines 35. So it means 75 of those particles has a weight that is 35. In this case, we're going to measure it in the as U, because we're going to represent our weight as U. And then this will be plus 25 of those particles will have a weight that is 37 U. So once you have this taken care of, we can then go to the next step, which means you can either collect like terms. In this case here, we have 25 taken out, and inside the bracket we have 3. Remember that will be really crucial. And this is 35U plus 25 is taken, and you're left with 37U. So once you have this, take note that it is over 100. So which means here that 25 is divided and you get 4, and therefore in here we have 3 multiplied by 35U plus 37U over 4. Now, this is where things get interesting. We're going to stop here for now, and let's look at the other method right here, which involves using ratios. And for using ratios here, we know that the ratio is 3 to 1 in terms of considering the specific isotopes, calcium or chlorine 35 and chlorine 37. Therefore, we know that the total of particles here is equal to 3 plus 1, which is 4. Therefore, once you have this taken care of, we can actually go directly from 3 to 1 ratio and the total to actually our average. So it means here that we need to take into consideration that 3 of the 4 particles actually has a weight that is 35 U, plus out of 4, one of them actually has a weight that is 37 U, and this is divided by 4 because we have a total number of particles to be 4, and this here is actually equal to our average atomic weight for chlorine. So average we just abbreviate it as A, atomic weight for chlorine. So once you have this written, what you notice is that, hey, you see we have the same expression, where for this part here, if you go through the percent method, you actually get the same expression as what you have for the ratio expression. So in here, you're able to actually determine what the AMU using both methods is, which means what is the atomic weight of chlorine. And the atomic weight of chlorine, when we assume that we have only those two isotopes, is actually, if you put all this into your calculator, you're going to get around 35.5 U, or 35.5 grams per mole of chlorine. And in this case, you can say of chlorine in this particular part right here. So it means that for 1 mole, which we know that 1 mole is equal to 6.02 times 10 to the 23 particles of, in this case here, chlorines, the weight of these particular particles will be, of chlorine, will be 35.5 grams in this particular process that we went through. So in this particular video here, you're able to actually explore this particular method, actually two methods, one involving ratios and the other one involving percent, in order for you to actually determine the atomic weight of, in this case, chlorine. I won't call it molecular weight because in here you're not building molecules, you're focusing mainly on atoms, and the same atoms, although different in terms of the number of neutrons, they do have a relative abundance which is actually measured using this particular method, which is actually called the atomic weight. And the atomic weight is usually found on the periodic table, where you actually have decimals, and they are never whole numbers because some isotopes are actually accounted for more in abundance in nature than other isotopes in nature. So that's about it for this particular video. I hope this video gave you insight on the two ways to solve this. You're able to actually develop a plan, you know, a little bit about how mass spectrometer actually, or mass spectrometry actually works, and how this is actually rightly important in determining the atomic weight of chlorine, and this is applicable to other elements on the periodic table. Take note that the assumption here is that you are given only two isotopes of chlorine. There are way more isotopes of chlorine, but for this particular example, you're given the ratio and you're asked to, hey, what is the atomic weight? So there are two ways to go about it. Either you use the ratio method, where you just get your answer directly, or you use the percent, where you actually go from ratio to percent, and from percent you actually get to the common expression that you will also get from the ratio method, and from there you'll be able to get your atomic weight for any specific element right there. So thanks for following me through this. Truly appreciate it. Please hit a comment down below, let me hear your thoughts, and also don't forget to subscribe. By that way, I can talk to you all soon. Stay smart and believe in yourselves.